you can think of this next chapter is this is where we have mechanisms that start coming along. This is where the molecularity, you guys remember that from Gen Chem at all? Kinda, maybe, vaguely. Okay, so this is where we'll actually start having like reaction mechanisms, and that'll start being a thing. And so the exams after this point are going to start having mechanisms on them. And so they'll have drawing sections. Okay. And so the first thing we're going to start with is actually the common elementary steps. Think of these as like your little building blocks, your little Lego blocks that you build these reactions out. Okay. So these are a good way of understanding. By the way, this is like one of the most important things for biochemistry that you're going to want to take on over to biochemistry. Okay. Because every biochemistry pathway in all biochemistry situations are just combinations of the elementary steps I'm going to show you here. If you understand the elementary steps, there's actually very little memorization you need to do. In fact, the enzymes are largely just called the substrate plus the specific naming for that elementary step. So there's actually, you can really get away with very little details that you memorize about biochemical pathways, as long as you understand the elementary steps very well. Okay. Also, there's very little information in this course that you have to memorize past this point, as long as you understand the elementary steps right. Okay. All right. Now, one of the important tools that you're going to need, all mechanisms are predictive, of course. They're built out of the things we've already taught you. Okay. And so like proton transfers, when you have two charges next to each other, what's going to happen? Be attracted to each other, right? Does a bromine suddenly come into existence? Yeah. By the way, if you try to use AI in this course, be really careful that you actually look at it, because like it will just randomly have like no nitrogen, all of a sudden nitrogen, and then no nitrogen again, and all of a sudden nitrogen again. And there'll be like magic appearing and disappearing nitrogens and all sorts of things. Okay? Because it has absolutely no idea what's doing, right? Okay, so the opposite charges, these attract, likes repel, of course. Atoms in the first and second rows of the periodic table has to obey the duet and octet rules, respectively. If we're on the third period and lower of the periodic table, we can have the extra octet occur, right? Where we have more than 8 electrons. And that's because those have our d orbitals available. Okay. This right here is going to be, again, those arrows that I was talking about. So these are referred to as curved arrows. The fact that they have the 2 blades here means that 2 electrons are coming. And it's always the electrons moving from one place to another. Okay? You never move atoms around because atoms have weight, right? We move the electrons, and then the next step has atoms moved. Okay? Okay, and so this is your electron-rich site here. Well, where do electron-rich sites have to go towards? They have to go towards electron-poor sites. Okay? They don't go towards other electron-rich sites, right? If you were digging a ditch, a gully, would you dig uphill so that your water can flow? No, that's not going to work, is it? And the same thing happens here. If you dig uphill and point your arrow to an electron-rich site, well, the electrons are not going to flow there, right? Because that's higher energy. Okay? So these are very self-consistent, predictive. Okay? The things you already know is what these are. We're just putting them into steps so you can more quickly string those together. Okay? Okay, so we're actually seeing the acid-base reaction we've normally done, which is NaOH plus HCl. And so our electrons go and get donated to the electron-poor H+. That's going to form a new bond, which is what we're seeing right here. We rewrite these structures with our new bond and our separation now accommodated. The electrons within this bond here have to go on to chloride because we're moving 2 electrons into a bond with the hydrogen, right? Well, it can't have 4 electrons on it, can it? And so the electrons in the bond that was with it have to move off onto the other atom. Okay? Okay, and that's what you get for a product. Can I have a difference in charges between two sides? The sum of the charges between the two sides? That's my electrons, isn't it? I can't have electrons pop into existence, can I? Okay. So whenever you look at these, keep that in mind. Like you have to have the same number of hydrogens on both sides, oxygens on both sides, chlorines. You have to have the same number of electrons. That means your charges have to be the same on both sides. At least the total has to be the same. Okay. So for example, I could have a neutral charge on one side, but if I have a positive charge on the other side, then I also have to have a negative charge there, don't I? Because they have to be the sum has to be the same on both sides. Okay? I have to have the same total number of electrons, same total number of protons. That means same total charge. Okay, let's try this right here. So let's identify the electron poor hydrogen atom in this methanol molecule. Draw the mechanism by which a methanol would act as an acid in a proton transfer reaction with H2N. So make sure you actually draw these out, because otherwise your brain is going to self-justify things. By the way, do you guys know how decision-making actually happens in a brain, according to all the new MRIs, the fast MRIs? So as it turns out, you do, and then you go through a whole process of justifying why you did that. So you think you make decisions, but in reality, the parts of your brain that don't talk to themselves make the vast majority of decisions. And you just self-justify why you did it. And funny enough, most of your mood is actually controlled by mitochondria and your gut bacteria, which are the two parts you probably don't think of as you. So we're just like these puppets being controlled by our gut bacteria and mitochondria. And our math side of our brain that's quiet and doesn't talk to itself is the silent passenger. The other side of our brain that talks to itself is like, I did this because of this. Then you do something again, you're like, I do this because of this. It's just total BS justification. Yeah, but you can train yourself, so that's positive. Anyways, okay, everybody ready? Okay, not gonna self-justify later. We've committed. Fantastic. Okay, now, what are the electron poor areas? Well, your hydrogen's your electron poor right here, right? That's going to be your most electron poor. Your most electron rich area is probably going to be right there, right? That would have your partial negative charge. Okay. And so if we look at that N minus, right? Well, N minus is quite electron rich, isn't it? Okay. And so we would very much expect that N minus to react with our electron poor hydrogen, wouldn't we? Okay. So which direction do the arrows go? Do they go from hydrogen to the nitrogen? No. They go from that lone pair on the nitrogen to the hydrogen. You're perfectly correct. You got it. And so once they flow onto that hydrogen, well, that's going to make the hydrogen have too many electrons, isn't it? And so the bond that the hydrogen had before has to go onto the oxygen, which was your electronegative atom, right? And so you're going to rewrite it on the other side with an arrow, of course. And that's going to give you the negative charge on the oxygen. And you're going to have a neutral charge on that nitrogen now, aren't you? Everybody get that okay? Is anybody confused why it looked like that? Fantastic. Okay, so let's simplify some assumptions regarding the electron-rich and electron-poor species. Anions do not exist in solid or liquid phases without the presence of cations and vice versa. These are assumptions. They're not 100% true, but overall in bulk, they are true. Okay? So anions do not exist solid or liquid phases. Metal cations are typically going to be behaving as spectator ions. This is generally true in group 1A. And so when you see lithium, sodium, potassium, they're typically just spectator ions. They don't really do much because they're the thing that everything steals electrons from all the time because they have some of the worst electronegativities on periodic. Okay, and so if we look at like sodium hydroxide here, you can actually just simplify this to be sodium plus spectator. I don't have to worry about it anymore. And then hydroxide, OH minus. In organic chemistry, whenever we're doing organic chemistry, we have a big tendency to just drop spectator ions and no longer care about them at all. Okay. So from now on, you should pretty much expect if I say NaOH, KOH, something like that, you're going to be like, where'd the sodium go? Where'd the potassium go? And I just don't care about it. Like, whoop, there's spectator ion. Okay, where it's gone. All right, now draw the necessary curved arrows for the proton transfer between KOCH3 and HCN in solution. Did we have a spectator that I'm going to kick out of this? We do, don't we? Yeah. Enjoy your spectator ions. This is probably the last chapter you're going to see them again. And they're booted out of here. Never to be discussed again. Unless you start talking about sodium pumps in biochemistry. Then it's discussed. Is everybody committed to your answer, or is people still? That answer. Okay. I think everybody's kind of gotten enough that they can go forward. Okay. So, spectator ion, potassium, right? Boot it out. We don't need to really talk about it much anymore. Okay. That's going to leave us with the OCH3 minus, right? Negative charge on the oxygen. Okay. Okay. And so that's ionic. That is a base, very strong base, actually. It's very similar to OH minus and how it reacts. Okay. And so the next thing we have to do is we have HCN right here. Oh, I have the wrong thing here. But yeah, copy paste, right? Tables are a pain to set up, okay? Okay. Your HCN then has to be your acid, doesn't it? It has a hydrogen on something that's going to be kind of electronegative. Okay. And so we go ahead and write those out. This is going to be your base, the electron-rich site. This one right here is the electron-poor site. And then the CN has a triple bond, by the way. Hopefully everybody figured that out. That's one of the reasons why this is a reasonably decent acid, is because it's sp hybridization. Okay. And so the electrons flow from the electron-rich site to the electron-poor site. That's going to cause these electrons to start bumping over. they're going to have to bump over onto the carbon. Why doesn't it go into a bond here? And the nitrogen can't take on more electrons, right? So if the nitrogen here had more space to take on electrons, it could flow into a bond. Okay, but in this case, it just does not, right? This is already going to have a lone pair here, so it's maxed out. Okay, and so it flows onto the carbon. That's going to leave your carbon with a negative charge here. So we did the numbers of electrons. We didn't bother putting in the lone pairs. Because nitrogen. Huh? Yes. Yep. Yep. It would end up with lone pairs here and right here. Now, interestingly enough, this would have a pretty interesting inductive effect. And this does share some of the electron density with the nitrogen. So it does make that nitrogen a bit more negative. Okay, so let's talk about organometallic compounds. Now, we've talked about metals that we can just kick off and ignore. But not every metal is going to be one that we can just kick off and ignore. Some metals actually do form covalent bonds. Okay, you may have noticed back in your general chemistry days, like if you looked at the periodic table, and it mentioned ones that always form ions, that mentioned ones that can form covalent bonds. Most of those covalent bond makers are then the transition metals. Most of them. But there's a few outside. Okay. So organometallic compounds are going to have metal atoms that are bonded directly to a carbon atom, and that's why they're called organometallic. Organo is in carbon. Okay. The carbon metal bond is going to act as a polar covalent bond, and so it is a covalent bond. It's going to have dipoles, right? It's going to have charges on it because carbon is more electronegative than most metals. Oh, well, all metals, really. Now, the carbon is going to be more electronegative, of course, than the metal. This is going to give you something that you can treat as an electron-rich carbanion. Because carbon is significantly more electronegative, these bonds break fairly easily. And so you effectively, in most of these reactions, just have very electron-rich carbons. Okay. Metals are going to be quite stable as their cation forms, as you've experienced throughout general chemistry, right? Fe3 plus, Fe2 plus, etc. Now, this is a carbanion, by the way. That's simply a carbon that has a negative charge and a pair of electrons on it. Okay? And so this would actually be a carbanion. This is actually how you can abstract these organometallic compounds and sort of think of these as. So you don't have to go organometallic this, organometallic that, and, oh, what is this going to do a different reaction? No, it's just going to, they're all going to act like this. Okay? They're all going to act like they're negatively charged electron-rich carbons. Okay? It's just carbon's not electronegative enough to actually exist as a carbanion for any significant periods of time. Okay, so these are different examples, actually. And so, anybody ever heard of like lithium, as in lithium you take for psychotic episodes? No? Nobody? Okay. Yeah, very, very common drug for people to take if they have various different mental diseases and illnesses. This is actually the type of lithium you would see in that. It would be a lithium that's actually an organometallic compound. And that's actually why it works. If you were to take like lithium chloride, it actually wouldn't work very well. It wouldn't absorb. Anyways, this one's a Grignard reagent. This is a lithium cuprate. It's kind of an interesting one. But again, all of these, you can kind of just ignore the fact that they have the metals there and treat them as if they're the carbanions. Okay? And so negative charge, lone pair, wherever that metal is. Okay? and then you just sort of treat them as if they're that. Right? And so this is going to have a methyl that has a negative charge here. This one's going to be an ethyl with a negative charge. This one's going to be that benzene ring with a negative charge. And that's a great way to simplify it. You're going to be right 99% of the time, and it's not going to be an issue at all from this time. Hydride reagents, these are going to function as a very common, extremely powerful reducing agent. So these are incredibly powerful because you may have seen that hydride is very powerful base. These are going to include lithium aluminum hydride. This is the abbreviation for that, Li, lithium, Al, aluminum, and that has 4 hydrogens, hydride. Sodium borohydride is also a fairly common one. And so this is going to have NaBH4. That's how you write that out. And so this is kind of what they look like. The metal ends up being a spectator ion. This right here is going to end up being a negatively charged anion. This anion here actually can be simplified further because you can disregard this metal portion and just write it as a hydride. Negatively charged hydrogen with a lone pair. Okay. Now, again, this would not be stable enough to exist on its own. This is kind of like when we talked about acid-base solutions and we write out H+. We don't actually have H+. We have H3O+, right? It's the same thing. Okay? And so we're going to write it as H- with a plus. That's your electron-rich portion. This is that borohydride, by the way. Notice that this is actually a very kind of interesting compound if you start thinking about this, because boron typically only makes how many bonds? It makes 3, doesn't it? So what's happening here is it makes its normal 3, and then it actually has a coordinate covalent bond made to it. Do you guys know what a coordinate covalent bond is? It's where you have a pair of electrons that goes into a bond with something else, and so only one of the atoms provides the electrons for it. It's the type of bond you've been seeing for like the acids and bases, where you have a proton coming on to O-, right? And so the proton doesn't provide any of the electrons for that. Okay, so let's talk a bit more about molecularity and talk about these elementary steps. So this one right here is going to be a bimolecular nucleophilic substitution. Okay, it's going to be labeled SN2. Can everybody see that? You have the pieces to it, don't you? 2 for bimolecular, N for nucleophilic, S for substitution. That name tells you everything about this. Okay? Like if you don't remember anything about this and you just remember the name, you can work your way through this problem, right? I know because I did. I told you about how I learned this, right? I mean, you don't get a chance to study if you take an exam every week. Forget studying. Heck, just reading the materials. So, in a SN2 reaction, what we're going to see is, do you guys remember your molecularity back from Gen Chem? So back in general chemistry, what they were teaching you is, remember the rate laws that you guys did? And it had first order, second order, third order? Okay. You never saw third order? Because it doesn't exist. Okay. First order and second order, though, you saw those. Okay. Now, those orders were based on the slowest step, right? Remember that? Okay. That slowest step was elementary steps of the reaction. Okay? When you summed up all of the steps of reaction, you get a mechanism, which is what we're heading towards right now. We're heading towards how do I write out those mechanisms and predict them. Okay? Okay, so these elementary steps, those were where you got the orders from. Those orders were called molecularity. How many things have to collide in that reaction for the reaction to occur? Okay, so in the case of a bimolecular reaction, we have to have 2 things. They have to collide together. Okay, everybody okay with that? Okay. If we have a unimolecular reaction, what's that going to be like? How many things have to collide? Yeah, we just have one thing. It's going to be by itself. It's going to do its thing. Okay? And that's always going to be your slow step. Okay? Okay, so if we have this case, bimolecular, two things have to collide. We're going to have an attacker and attackee. Okay? And we have a very specific naming for these attackers and attackees. Okay? This is going to be your nucleophile. Your nucleophile is a nucleophile because it has what's the charge here? Negative charge. If it's negatively charged, what does it want? What is it like? Positive. Yeah. Nuclei are positive, right? And so nucleophiles want positive charges. They want to attack something with a positive charge. Okay? And so this is a nucleophile because it has a negative charge. It's going to attack something with a positive charge. This can be referred to as an electrophile, or it can, in this case, be referred to as a substrate. Has anybody ever heard of a substrate before? Like proteins and stuff, right? Enzymes? Okay. Substrates are substrates because they're bonded to the thing of interest. Okay? So they're the thing you're attacking, they're the thing you're binding to. Those are substrates. Okay? So this is a substrate, but you could also just as easily and well call this an electrophile because this is slightly positive carbon here, right? Everybody okay with that part so far? Okay. Okay, so you have your electron-rich area right here, right? Your nucleophile. It's going to attack the electron poor area. This is going to cause the bond that's already on that carbon. Well, that has to break, doesn't it? Because we added 2 more electrons. Okay? This is going to go onto the more electronegative thing, the thing that holds that negative charge better. And those are those same cardinal rules, right? Okay. And so this is going to be what's called the leaving group then. Because in this case, we're substituting something. So that's why it's called substitution. We're attacking with a nucleophile, and then we're going to have another group leave. And so we substitute a different group. Okay. So when you have, let's put it all together. Everybody ready? We have our SN2, right? You have a nucleophile. It attacks electrophile. A leaving group leaves with that electron density. Okay? Everybody okay with that so far? Okay, very good. Notice again, they have the same steps. It's the same thing every time. You could have just put like R's everywhere else, except for where you actually care. And you could have just labeled these L for leaving group every time. As long as you understand that, like, this one has resonance charge, right? So it's very stable when it leaves. This one's chloride. It's very stable when it's a negative charge and leaving. Okay. And so here we have our nucleophile again, negative. We have a lone pair of electrons here. We don't actually have a negative charge in this case. It's going to attack our electron deficit area, where we have an electron poor. And then this is going to cause the bond to go onto this oxygen here, because we're making another bond to this one, right? So it has to lose one of those bonds. It's the thing that's attached to something electronegative. Same way as you did dipoles. Remember where you did polar, nonpolar back in Gen Chem? That exact same thing. The partial charges that we did. So ones with partial charges, that'd be positive. Okay. Is that making more sense? So this one, it's not bonded to something that's electronegative. So there's nothing pulling electron density away from it. Okay, let's quickly go back through poles. Okay, so when you did poles back in general chemistry and when we talked about the beginning of this course, what you are looking at is a difference in electronegativity, right? So if we have the same 2 things bonded together, this is going to be nonpolar, right? Okay? And that has no dipole, right? Okay? If we have something that's a little different, this is going to have very small holes, right? But this is a very small hole. Right? If we have something that is much more electronegative, like a chloride, this is going to be a much larger hole, right? And so this is going to have a partial positive charge here, partial negative here, right? This means this is electron poor. Why it, this right here is negative because it's electron rich. And again, what determines that is electronegativity. Right? Electronegativity being how well you pull the electrons. Does that make more sense now? This one right here? This one? Yes. So it would be slightly more positive than like a completely CH3 somewhere else. But this is going to be the one that's very electron poor, right? Because it's directly bonded to that oxygen. In fact, it's even worse because this is bonded to a bunch of other oxygens. And so this is going to pull electron density through this whole structure. Okay. Yeah. Same thing here. The chlorine is what makes that electron poor. Okay. No problem. No problem. You can also think of these like vacuums, by the way, where you have like a lot of density and then it floods into the other area because it has a lack of that density, right? Or like ditches. Those are good mental models. Okay. So again, this is going to make this form. Notice, by the way, that if we do not have a negative charge at the beginning here, we're going to end up with a positive charge here because we'll have a negative charge on the other one, right? The Levy group. And so see how our charges are still, the sums are still the same? That's very important. Something really tricks a lot of students when they're learning this, okay? And causes a lot of problems for you. Okay. Did that take care of that? And everybody's up to date and current and looking good? Okay. Remember that SN2, okay? So that's our first elementary step that we're really focusing in on, other than our proton transfers. Right? Okay, so this one right here is our free energy diagram of our SN2 step. And what you notice here is we're going to have that nucleophile. It's going to attack the electron poor, usually carbon, right? And then what a leaving group is going to leave, right? So here we have our reactants. Now, when it attacks, though, it's not like it just kaboom, and then you don't go through any steps in between, right? You have to go through all the steps in between. So if you start thinking about this, right? If you have something, you're attacking it, and then pulling it away, there's a middle space where both of them are tugging, right? And so we're going to have this energy barrier here. This is going to be where you actually break all of that. Remember your sp3 hybridization and your wonderful structures, all of that. You actually have to break that, okay? And so what's going to happen is these electrons are going to flow into this electron poor carbon, right? They're going to start forming a bond. While it's forming a bond to this carbon, the previous bond is going to start breaking because it's going to lose that attraction because you got this negative charge starting to build up there, right? And so the leaving group is going to start pulling those electrons away, and you're going to end up in a very high energy transition state. That's this right here. That looks like this. With two partial bonds, we'll have two partial charges to it. Then that's going to fall apart. Now, can it fall apart back this way? Yeah, we definitely can. In which case, you make your reactants back again, right? Nothing happens, okay? If we fall this way, it's going to end up with the products. The leaving group will leave. We'll have our nucleophile substituting there now, and we made our products. Now, notice that going backwards in this reaction is going to be much harder than going forwards. Yep, you got much larger energy barrier, don't you? This is what is referred to as irreversible, by the way. So a reversible reaction, the energy barrier is about the same on both sides. Yeah, so you can go over both sides, easy enough, no problem. Irreversible, the energy barrier is much larger on one side. So you can't go backwards. And that's it. That making sense? Okay, I am out of time. We will start next time on the next one, characterizing the substrates. Okay. Okay. Now, I've been kind of making the point of like nucleophile, same as base. Notice that, yeah, a lot of the things about nucleophile and bases are going to be the same, but there are going to start being differences. Okay. So don't let that stick in your head right now that they're the exact same thing. Yeah, go for it. You have one.